It's time to get started on what some may call a hardcore organic topic. It's all about the shapes of molecules in 3 dimensions. And that's what we're getting started on today, and we'll continue studying all this week. Here I have for you an sp3 carbon, a tetrahedral carbon, and it has 4 different groups on it. The reason I say that is because they're 4 different colors. Let's draw this molecule on a flat piece of paper. So if I start off with a carbon, I'm going to make it a black carbon. And I'm going to try to look at this where pointed straight up, what I would say is in the plane, is really difficult. Pointed straight up in the plane is a hydrogen that's white, or a thing that's white. And pointed straight over here in the plane, there's room below this paper, over here is something that's blue. So if I point straight up, we have the white dot. Over here is something that's blue. Note that the angle between this white and blue is not 90 degrees. It's greater than 90 degrees. It's an obtuse angle between this white thing and blue thing. There's plenty of room beneath this paper. This white, black, and blue are all in the same plane. If what I try to do next is draw this red thing is actually touching the paper. It's pointed backwards. The way that's drawn on a molecule is with a dashed bond to the red thing. So then finally, if we look at this green thing that I've been holding on to the whole time, it's not in the same plane. The rest of these, this white carbon, this white ball, this blue ball, and this black carbon in the middle, the rest of these are all in the same plane. And the green is coming out toward. Can you tell that green is coming out toward? Hopefully. So the green thing is coming out toward me. That's a big, bold, dark line, and that's green. That's this 3-dimensional molecule that we see. Could we have drawn it looking at the red and green in the plane? Sure. You could point it this way if you wanted to. Red would be kind of up and to the left. Green would be straight down. The angle between them is obtuse. The angle between the blue and white is always acute. The blue and white should always be close together because they're pointed the same general direction on the actual tetrahedral molecule, and it tells us the proper representation around this tetrahedral molecule. You can draw molecules like this from many, many perspectives and still be a representation of the same molecule. Seeing things in 3 dimensions is not always students' favorite thing. It's a tough topic. Before we go back to paper, one of the things we will have to do is view multiple molecules in 3 dimensions and different perspectives and try and decide, are they the same molecule or not? If you simply compared these 2 molecules, you might think they are the same. One of the ways we're going to have to decide if they are the same is imagine picking up one and trying to align everything perfectly on another molecule. If they align, then they are the same molecule. There's a lot about these molecules that do align, but there's some that don't. The red carbon and blue carbons are now on top of each other. Blue and blue, blue and blue, that looks great. White, white, green, green, that looks great. Uh-oh, green and white, green and white. That's not great. We need to be able to look at 2-dimensional drawings like of these molecules and tell, are they the same or are they different? Because they're going to have potentially different properties. And there's a lot of definitions that we'll talk about throughout this unit. You may or may not have noticed in those molecules I was just playing with, I ended up having to rotate one molecule to match the other, or to try and match the other. The act of rotating things or changing the way they look a little bit is called conformations. Because alkanes have all single bonds, rotation can happen around all single bonds. So rotation will get us different perspectives to look at the same molecules. There are three main ways that we draw these organic molecules. This top one is called a perspective drawing. The middle one is called a sawhorse, and the bottom one is called a Newman projection. All of these molecules are simple ethane. 2 carbons, all single bonds, fill it up with hydrogens. This perspective drawing, this perspective is different from that perspective in that you've rotated the right-hand carbon by 60 degrees. We'll talk about degrees and stuff a little bit, but you've rotated this carbon to be a little off kilter from what it was before. How do I know that? This hydrogen and that hydrogen are in the same plane, both pointed upwards on the leftmost structure. The hydrogens that are in the plane are up and down on the rightmost structure. And the ones that are coming toward me are both pointed down. The one coming toward me is pointed down and up. Those are different perspectives of the same molecule. All that has happened between the left and the right is rotation. Exact same scenario in the bottom, or in the middle sawhorse. You've rotated the front carbon this time. Well, to me this looks like the front carbon. It kind of depends on exactly what perspective you see it from, but we've rotated one of the carbons. To me, this is the front, but we've rotated one of the carbons to be a little off sync from the other. Newmans, exact same. We've got 2 hydrogens in the same plane. I should actually point out first that a Newman projection is looking down a bond. So looking down this bond from a side angle. So this one carbon is directly in front of another. That's what this central circle is. It's one carbon directly in front of another carbon. I'll pull out the models again in one moment. But this Newman, all the hydrogens are on top of each other in this one. You twist the back one, and you've got the front one staying the same, and the back hydrogens are a little off sync from what they were. All of those molecules are ethane. All of them from left to right, you've tweaked one of the carbons and only one of the carbons. These are simple molecules. We're not going to spend a ton of time on simple molecules, but we are going to spend a little bit of time because the better your foundation on the simple molecules, the better understanding you will have when we get to the complex molecules. So here's ethane, simple ethane. We could look at it from different angles and draw a perspective, a sawhorse, etc. But let's talk about Newman. A Newman is going to look straight down a molecule, straight down a bond, so that one carbon is eclipsing, is in front of another carbon. You can see my finger pointing at something, but you can't actually see that other carbon back there. It's back there, but we're choosing to look at it from a perspective where one is directly on top of another. That's a Newman projection. If we look quickly, I'm going to pull it a little bit where you can see the back carbon some. I've got a red hydrogen, we'll say it's a hydrogen, this is ethane. I've got a red hydrogen pointed up and a red hydrogen pointed up on the front carbon and the back carbon. I can go through different energetics when I rotate one of these carbons. I'm choosing to rotate only the front carbon, not the back carbon, but I can rotate 60 degrees and until I get to a full 360 degree rotation of ethane. When ethane is in this kind of perspective, that's called eclipsed. That's not great energy. This is a big, sizable molecule, but electrons, remember, are negatively charged and they repel each other. So these electrons in this cloud holding on this hydrogen over here, and those electrons in that cloud holding on this hydrogen down against the paper, they're actually very spatially close to each other, and that's not great. They repel each other and they want to twist to get some relief so that they're not so close to each other. This is the best relief that they can get. They can be 60 degrees from each other. So my front carbon is just 60 degrees off turn from my back carbon. That kind of conformation is called staggered. Remember, this one was eclipsed, staggered. If I rotate 60 degrees more, eclipsed again, and then staggered. Whoops. Eclipsed again, and then staggered, and then finally back to my eclipsed form that I started with. So there are two main conformations of ethane, two main Newman conformations of all the molecules that we'll look at in Newmans. Let's look at it on paper. So here's the textbook drawing of the rotations that I just showed you in ethane. Starting over here with the two red hydrogens up in an eclipsed conformation, and then the two red hydrogens askew. What's different about what I showed you versus what's here? What's here, the back carbon is what has rotated. The back carbon has rotated 60 degrees clockwise. And then I get back to eclipsed, staggered, eclipsed, back where I started. Does a conformation between 0 degrees and 60 degrees exist? Yes. Anywhere along that axis as the twisting motion is happening is called a skewed conformation. But we're only really worried about the hills and the valleys. The hills are the eclipsed, the valleys are the staggereds. Staggereds are always more stable than eclipsed in a given molecule. This is what I was describing. Those electrons don't like each other. That repulsion is called torsional strain. That's why it wants to twist to become staggered instead of eclipsed. The repulsion between those electrons. More energy is required for rotation of propane than ethane. What would a Newman projection of propane look like? Let's talk a specific or two about drawing a Newman. I draw a circle, and I unite three groups in the center carbon, in the center of that circle, to represent the front carbon. The back carbon has three groups coming off of it, but those groups only hit the circle, they do not come to the center. So if this is propane, without pulling out the model kit again, propane is going to have three carbons. Every Newman projection only represents two carbons. So if I have a CH3 as one of these positions, then my front carbon here is going to be a CH2, and my back carbon back there is going to be another CH3. That's propane. Propane doesn't have a lot of interesting things about it, so we're going to talk about it quickly. Is that a staggered or eclipsed conformation of propane? Staggered. If we wanted to draw the two limiting, that means we also need to draw an eclipsed version of propane. I'm going to keep my front carbon the same. It doesn't matter which one you rotate, but you're going to need to rotate the front or the back. If you're going through a whole sequence, make sure you're consistent rotating one or the other. So if I choose to rotate, let's say, my back carbon clockwise, that means this H is going to come down and be here. They're technically totally eclipsed, but it's real hard to draw one line right on top of the other, so I'm showing that they're really close, but they're technically eclipsing each other. This hydrogen that's a back hydrogen is going to come be in line over there. That's this hydrogen. And this hydrogen is going to go up there to be eclipsed with the methyl. To me, it's easier to make the bonds a little bit longer sometimes, so there's not quite so much overlap. But you're trying to show that these bonds are really snuggled close together on all 3 points around that circle. And remember, this is my eclipse conformation. Ethane and propane are nice, but butane is much more interesting. Here is butane. Butane is a much bigger molecule. It's a little bit hard to get in my whole camera view, actually. But let's draw Newmans of this butane. But before we get started drawing, let's actually look at the rotations of it. You could look at butane down the carbon 1, carbon 2 bond. That's these on my thumb and middle finger. You could look at it down the carbon 3, carbon 4 bond, or carbon 4, carbon 3 bond. It doesn't really matter when you look those ways, but if you look down the carbon 2,3 bond of butane, you can get some interesting Newmans. Let's not make us all seasick here. But if I look down carbon 2, carbon 3 in this butane, carbon 2, carbon 3 in this butane, I'm saying carbon 2 is my front carbon that has blue stuff on it. Carbon 3 is my back carbon that has red stuff on it. I'm going to start out in my drawings in this perspective. Blue CH3, see that the whole CH3, it's giant. Blue CH3 pointed straight up on carbon number 2. Red CH3 pointed straight up on carbon number 3. Then I'm going to tick. We'll do the front because it's easier on my model. I'm going to tick 60 degrees here. Red carbon stays the same back there, pointed straight up. And my blue carbon changes to be pointed, 2 o'clock, 1:30, something like that. 60 degrees more. There's my eclipse conformation. And my blue methyl way down here. Rotating the staggered. This one's the worst, hardest to see. I'm going to have my blues pointed straight down while my red stays straight up. 60 degrees more. 60 degrees more. And then I'm back where I started. I'm not sure you got much out of me rotating that, but it made me feel good to do it. Let's draw it on paper. So I'm going to start with a black circle to represent my front carbon 2. And I'm going to go ahead and draw black bonds, although they really maybe could be, should be blue for representing my front carbon. We'll see. If I'm going to start with the first conformation that I was in, that's eclipsed. So I'm going to draw my template Newman projection as an eclipse conformation here. I can fill in my blue CH3 up top and my blue hydrogens on the front carbon. Make sure that your hydrogens on the front carbon are coming off of those bonds. The red CH3 is on the back pointed straight up, and there were 2 red hydrogens on the back carbon also. So if I stick with what I did in my model, I can rotate my front carbon clockwise a 60-degree tick. Back carbon stayed exactly the same the whole time. Front carbon rotated where I had a methyl over here at 130-ish, remember? Yep, grandpa. And my 2 hydrogens rotated around with the methyl. Methyl went this way by 60 degrees. Blue hydrogens went that way by 60 degrees. Let's do it again. Back one stays the same the whole time. I could, in fact, go forth and draw templates at this point. Wow, these are great circles. Aren't they great? I even have computer at hand, and I did not choose to draw a perfect circle using the computer. But my back stays the same in all of these, so I'm going to go ahead and fill out the back bit in all of these. Oops. That's not a methyl. That's a hydrogen. And it's the blue carbon, the front carbon, that changes. It changes to be down here, and the hydrogens follow along because they're all connected to the same carbon. And I'm going to go from here to my molecule over there. My methyl pointed straight down. Hydrogen, hydrogen. Methyl over here. Hydrogen, hydrogen. And methyl here with hydrogens trailing behind. Okay, what does all this mean? Well, if I do use my actual circle now, I can circle all of the eclipsed conformations. It's a little bit messy, but maybe legible. And I can square my staggered conformations. Why would I do that? Because I said energetically, staggered is always more stable than eclipsed. So if I gave all of my structures a letter, we can talk about the energetics of these conformations. Electrons are negatively charged. They don't like to be close to each other. So A, C, and E are all lower energy than B, D, and E. Nope, F. Don't know my alphabet. B, D, and F. But numbering three higher than the other three is not good enough for us. Because if I compare A, C, and E, they are not all equally unstable. One is worse than the others. Who's worse? A. A is the worst structure because I have the two biggest groups right smack dab on top of each other in A. That's not the case in C. That's also not the case in E. So A is the highest energy conformation, period. C and E are tied for second place, as in the worst. Okay, what if I compared B, D, and E? Are all of those created equally? Nope, of course not. Which one of these is best? That would be D, because in D, I've got the two biggest groups as far apart in space as they can possibly be, and that's great. That's stellar. That's awesome. So D is the lowest energy, aka the most stable conformation, while B and F are equal stability because both of them have big groups right next to each other, 60 degrees from each other. Two big groups right next to each other, not great, but not as bad as eclipsed, but not as stable as when they're apart, when they're as far apart as they are in D. So this is what butane looks like. Butane and all these conformations of butane have some special names. Let's talk about these special names. So here are the neatly drawn conformations of butane, a little bit different from mine. We didn't start in quite the same spot as this one does. We started over here, but it will then follow in the same order that we did. So this A, B, C, D, E, F does follow the same pictures that we drew. So maybe I should actually label these A, B, C, D, E, F, because that matches our picture a bit better. All right, so I said each of these has a name. The most stable one was D. That one is called anti-periplanar. Why anti? Because the two big groups are on opposite sides of your conformation. Anti. Periplanar because all four atoms, carbon here, and here, that's front and back carbon, and carbon here, all four atoms are in the same plane. P-L-A-N-E plane. They're in the same geometric plane. You can slice through all four of those carbons at once. So that's called periplanar. Anti-periplanar. Anti on opposite sides, periplanar, all in the same plane. All four carbons, all four atoms connected around the Newman, all four big atoms connected around the Newman are in the same plane. Look. The two conformations where we had big thing 60 degrees away from the other big thing, that was this one and that one. Those groups that are 60 degrees away from each other are called gauche. G-A-U-C-H-E, gauche. Not ghost, but real close. Gauche. Gauche has another name as well. The two carbon groups are not opposite from each other, so they are not anti. They are known as syn, S-Y-N, syn. They are also not periplanar. You could not slice through all four carbon atoms here in butane all in one plane. So that's called clinal. So these two conformations are both called synclinal. Okay. Is there another one that we would call periplanar that you could slice through all four atoms with one chop? Yeah, this one. You could slice through, because they're officially eclipsed, you could slice through all four carbons in that butane at once. So that's called periplanar. But the two big groups are right on top of each other. That's not anti, that's syn. Syn periplanar. One more name, and it applies to both remaining molecules. The two carbon groups are kind of pointed in opposite directions this time, so we're going to call it anti. Not all in the same plane, so we're going to call it clinal. Synclinal, anticlinal, antiperiplanar, synperiplanar. Unfortunately, you need to be familiar with all of those words associated with butane and similar molecules around Newman projection. A couple of things to note. Staggered is always more stable than eclipsed. Gauche is bad news. There's a numeric value for how much a gauche interaction costs you, how much energy it raises the molecule by. If we have something other than a methyl interacting, so butane had a 2 CH3s, if it were a pentane, for instance, we would have a CH3 and a CH2 CH3. We would have a methyl and an ethyl interacting. So the numeric value for a methyl-ethyl interaction is larger than a methyl-methyl interaction. Whew. Synperiplanar, bad news. It's the worst of the worst. All right, let's look at a couple of problems. Use Newman projections to draw the most stable conformation for 3-methylhexane viewed along the C3-C4 bond. Also draw an energy diagram. So first, let's draw 3-methylhexane. Hexane means 6 carbons, a 3-methyl. We're going to need to specify one more thing about this guy, and that's whether that methyl is coming toward you or going away. So if I specify that that methyl is coming toward me, that means around this tetrahedral carbon, I also have a hydrogen, and that hydrogen has to be going away. So I'm going to go ahead and fill in that hydrogen going away. So we're going to view this along the C3-C4 bond because that's what my problem told me to do. I can't count. So I'm looking down this bond, C3-C4. And I'm going to go one step further, and I'm going to draw what's also hanging off of carbon number 4. So I have 2 hydrogens hanging off of carbon number 4, but because carbon number 4 is tetrahedral, one of those hydrogens has to be coming toward me, and one of those hydrogens has to be going away. Okay, cool. This is not easy to explain in person. It's certainly not the easiest to explain on a video, but let's try. If I stand over here, here's my eyeball. If I stand over here and I look down carbon 3, carbon 4 bond, that's going to make carbon 3 my front carbon and carbon 4 my back carbon. So I'm going to draw carbon number 3 as my front carbon, and from standing at my perspective over here and looking down that bond, I see carbon 2 pointed straight up in my perspective that I see. So I'm going to draw carbon number 2 pointed straight up. I'll give it a number. Carbon number 1 is directly connected to carbon number 2, but the position of carbon number 1 as far as what kind of angle it's at, whether it's pointed this direction or that direction, doesn't really matter because rotation can also happen around carbon number 2, so I just stuck it any old direction. Okay, then I have to know my left from my right. Oh boy. My left from my right. If I'm looking from this perspective over here, something that's coming toward me in a flat-looking perspective, this kind of thing in a flat-looking perspective coming toward me, when I change the angle of my head, or the angle of the molecule, depends on how you view it, when I change the angle of my head to view this, is this CH3 on my right or on my left? It's on my right. I hope you shouted that. It's real hard to lecture this. I'm going to put a CH3 over there. That's because on my left, I have a hydrogen that was going back away from me in my original perspective drawing. Whew, that's tough, I know, but I believe in you. You can do this Newman stuff. On the back carbon, I have a hydrogen on my left and my right, so I don't really have to worry about whether it's on my left or my right. And pointed straight down on the back carbon, I have an ethyl group, a CH2CH3 is what that actually is, CH2CH3. Notice on the top, I drew a line, a stick, and on the bottom, I drew a CH2, CH3. It doesn't matter what you write in a Newman. You can write it any old way. That is the most stable conformation of 3-methylhexane. What? How do I know that automatically? Because I drew my backbone in a zigzag. My longest chain was drawn in a zigzag form. Anytime my longest chain is in a zigzag form, it's going to be the lowest conformation. Because my two biggest groups, that's this ethyl and this ethyl, they're as far apart in space as they can possibly get. That's this ethyl and this ethyl. They're as far apart in space as they can possibly get. That's the best conformation you can come across. Are there any gauche interactions in this molecule? Yeah, there are. There's a gauche interaction between this group and that group. So this question also says draw an energy diagram. That's a little bit tough with the space I have provided myself, but we can give it a shot. Starting over with the molecule that I just drew, but a little more real estate to work with, I can do rotations of my molecule. That's going to mean 6 conformations. My circle's getting smaller and wonkier with every time. That last one kind of looks like an egg. I'm going to go ahead and fill in my back carbon to stay the same so that I can rotate my front carbon. Do you always rotate the front carbon? Nah, you can rotate either one, and maybe I should rotate a different one for variety's sake, but I've already got most of my templates done at this point. So if we fill in the front carbons going clockwise, just because, we get these 6 conformations. Once again, I've drawn these rather big, and it's hard to talk about drawing an energy plot when you've drawn them so big, but I really want them all on one picture together so I can be sure that we're following along. So on the x-axis down here that I can't label because it's too close to the bottom is degrees of rotation, and it's energy along the y-axis. So if I look at these conformations, which one did we say is the lowest? We said A is the lowest. That's the staggered, where the biggest things are as far apart as they can possibly get. So I'm going to put a little shelf with A on it. If I rank A, C, and E, because those are my 3 staggareds, A has 1 gauche interaction, C has, 1, 2 gauche interactions, and E has 1 gauche interaction. So A and E both have 1 gauche, but are they equivalent? No. A is a methyl-ethyl gauche. E is an ethyl-ethyl gauche. So E is higher energy than A, and C is even higher energy than that. So A, C, and E I ranked together kind of low because they're staggered, although my plot is really bad scaling down there. Okay, let me erase all that mess. So if I go through now and rank B, or compare B, D, and F, can you tell me who's the lowest energy of B, D, and F? Can you tell me who's the highest energy of B, D, and F? I see hydrogen, hydrogen here, and hydrogen, hydrogen here, and hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, all along F. So to me, that says in D and B, I have big stuff eclipsing big stuff more than I have in F. So to me, that says F is my lowest energy eclipsed conformation, but F must be higher energy than A, C, or E. Okay. What about between B and D? B has methyl eclipsing ethyl. D has ethyl eclipsing ethyl. Woo! D's the worst. The worst. We're going to put D way up high, and we'll put B lower than D but higher than F. And this crazy little plot over here We're going to connect like a little roller coaster. Woo, woo, woo. Yep, isn't it pretty? I'm going to erase the last structure just so we can make sure you see what you need to see on this plot. But it's just an energetic roller coaster to tell me as this 3-methylhexane rotates, it goes through all of these hills and valleys. And the hills and valleys that it climbs and slides down are all different sizes based on energetics. Whew, that was tough. I thought this was supposed to be a quick problem. This one should be much quicker. Is this conformation staggered or eclipsed? Well, obviously, it's staggered. Best name of this conformation? What that means is look at the big stuff directly connected to the Newman and name those positions. Those 2 black dots are on opposite sides, so I'm going to call it anti. And those 2 black dots are in the same plane as the front and back carbon, so I'm going to call it periplanar. Is this a high energy or low energy conformation? It's the lowest energy this molecule could ever get in. Anti-periplanar is the best. And then the thing we ignored already was to name this compound, as in IUPAC, name this compound. So we need to find our longest chain. Longest chain is going to be 1, 2, 3, 4, 5, 6, 7 carbons long. It's a heptane. Then I count and I have a substituent on carbon 2 and carbon 6 based on how I've numbered them. It can't get any smaller than those numbers, so that's acceptable. On carbon 2, I have a methyl. On carbon 6, I have a methyl. 2,6-dimethyl heptane. Yep. The end. Whew, I thought I wasn't going to make it.